Good day, everyone, and welcome to this course on logic and digital systems. This is Module 1, where we will be laying the foundation for our journey into the fascinating world of digital design. In this module, we will explore what it means for a system to be digital, how we specify and implement designs, the number systems that underpin digital electronics, the essential building blocks known as logic gates, and the mathematical principles of Boolean algebra that allow us to simplify and optimize designs. Our goal in this first module is simple: to give you the conceptual tools and practical knowledge required to understand and build digital circuits. By the end of this module, you should have a firm grasp of digital design basics, the role of number systems, the operation of logic gates, the concept of circuit characterization, and the use of Boolean algebra for simplifying logical expressions. Let us begin. Section 1: Introduction to Digital Design. To understand digital systems, we first need to answer a very basic question: what does it mean when we say something is digital? The term digital refers to information that is represented using discrete values rather than continuous ranges. In contrast, analog refers to signals or systems where values can vary smoothly over a continuous range. A simple way to think about it is this: a light dimmer switch that smoothly increases or decreases brightness is an analog device, while a light switch that is either on or off is digital. In electronics and computing, the discrete values of digital systems are usually represented using binary digits, or bits. A bit can take only two values, 0 or 1. This binary representation makes digital systems robust, predictable, and easier to design. Digital design refers to the process of creating systems, circuits, and devices that process information in discrete steps, primarily using binary logic. These designs are at the heart of modern technology: computers, smartphones, digital televisions, industrial machines, and even medical equipment all rely on digital logic. So when we talk about digital design, we are really talking about the methodical process of creating circuits and systems that use binary information and logical operations to achieve specific goals. Section 2: Specification and Implementation of Digital Design. Every digital system begins with a specification. A specification is simply a clear statement of what the system is supposed to do. For example, the specification for a digital clock might be: display the time in hours, minutes, and seconds, with the option to switch between 12-hour and 24-hour format. Once we have a specification, we move to implementation. Implementation is the process of taking the specification and turning it into a real design, either on paper, in a simulation tool, or as an actual hardware circuit. There are generally two approaches to implementation in digital design. The structured method: in this approach, the designer carefully follows a systematic process. The problem is broken down into smaller modules. Each module is designed separately, and then they are combined into the full system. This method is reliable and reduces errors, especially in large designs. The trial and error method: in this approach, the designer experiments with different possible solutions until something works. While this can sometimes lead to creative designs, it is usually less efficient and more error-prone than the structured method. In modern practice, the structured method is preferred, particularly for complex systems. However, trial and error still has its place in simple circuits or during the early stages of brainstorming ideas. Section 3: Digital Computer-Aided Design, CAD, Tools. As digital circuits became more complex, manual design methods became impractical. Imagine trying to draw the wiring diagram of a modern microprocessor with billions of transistors. It would be impossible without computer assistance. This is where computer-aided design, CAD, tools come in. CAD tools allow engineers to model, simulate, and test digital designs on a computer before building them physically. Some key benefits of CAD tools include: speed: designs can be created and modified much faster. Error detection: simulations can reveal mistakes before costly hardware is built. Optimization: CAD tools can suggest improvements in efficiency, speed, or power consumption. Scalability: they make it possible to design very large systems, such as microprocessors. Common CAD tools include simulation software like Multisim, Verilog, and VHDL-based environments for hardware description, and FPGA programming tools. These tools are indispensable in modern digital design. Section 4: Digital Logic Basics. At the heart of digital design lies digital logic. Digital logic is the set of rules that govern how binary values are processed. Think of digital logic as the language of digital circuits. Instead of words and sentences, we use logic gates. A logic gate is a small circuit that performs a specific logical operation on one or more binary inputs and produces a binary output. The most common logic gates are AND gate, output is 1 only if all inputs are 1. OR gate, output is 1 if at least one input is 1. NOT gate, also called an inverter, it flips 1 to 0 and 0 to 1. NAND gate, output is the opposite of AND. NOR gate, output is the opposite of OR. XOR gate, output is 1 if inputs are different. XNOR gate, output is 1 if inputs are the same. These gates are the building blocks of all digital circuits. Everything from a calculator to a supercomputer is, at its lowest level, made up of combinations of these gates. Section 5. Number systems in digital design. To work with digital systems, we must understand number systems. Since digital design is based on discrete values, the way we represent numbers is crucial. The most important number system is binary. In binary, numbers are represented using only zeros and ones. For example, the decimal number 5 is written as 101 in binary. However, binary is not the only system we use. In digital design, we also use octal system, base 8 uses digits 0 through 7. Hexadecimal system, base 16 uses digits 0 to 9 and letters F. BCD, binary coded decimal, represents each decimal digit separately in binary. Why do we need so many systems? Because each has its advantages. Binary is the natural language of machines. Hexadecimal is compact and easier for humans to read large binary numbers. Octal is sometimes used in digital electronics for simplicity. BCD is used in digital clocks and calculators because it represents decimal digits directly. Being able to convert between these systems is an essential skill for any digital designer. Section 6. Implementing circuits with NAND and NOR gates. Although there are many types of logic gates, in practice it is often convenient to use only NAND gates or only NOR gates. This is because NAND and NOR are called universal gates, meaning that any digital circuit can be built using just one of them. For example, a NOT gate can be built from a NAND gate by connecting its two inputs together. Similarly, AND and OR operations can be constructed entirely from NAND or NOR gates. This universality makes manufacturing simpler and cheaper, since only one type of gate needs to be produced in large quantities. Many real-world digital systems rely heavily on NAND and NOR implementations. Section 7. Digital circuit characterization. When we design a digital circuit, we cannot just consider the logic, we also need to think about how the circuit behaves physically. Some important characteristics of digital circuits include fan-in, the number of inputs a gate can handle. Fan-out, the number of other gates a gate's output can drive. Switching time, how quickly a gate can change from 0 to 1 or from 1 to 0. Propagation delay, the time it takes for a change at the input to appear at the output. Noise margin, the tolerance of the circuit to electrical noise without causing errors. These factors affect the speed, reliability, and scalability of digital circuits. For example, a circuit with long propagation delays may not be suitable for high-speed computing applications. Section 8. Boolean algebra. At this point, we have learned about number systems, logic gates, and circuit behavior. But how do we analyze and simplify circuits? The answer lies in Boolean algebra. Boolean algebra is a branch of mathematics that deals with variables that have only two possible values, true or false, or in digital terms, 1 and 0. Some key operations in Boolean algebra are AND, represented by multiplication or a dot, OR, represented by addition or a plus sign, NOT, represented by an overline or apostrophe. Two important principles in Boolean algebra are De Morgan's laws. These state that the complement of an operation is equivalent to an operation of the complements, and vice versa. This allows us to transform complex logical expressions. Canonical maps, these are visual tools used to simplify Boolean expressions. By grouping ones and zeros in a grid, we can reduce complicated logic functions into simpler forms. Simplification is crucial because fewer gates mean cheaper, faster, and more reliable circuits. Section 9, Conclusion of Module 1. We have now reached the end of Module 1. Let us quickly summarize what we have covered. We started with the meaning of digital and the difference between digital and analog. We learned how digital design moves from specification to implementation, and the methods used in design. We examined the importance of computer-aided design tools in modern practice. We explored the basics of digital logic, including logic gates and their functions. We studied number systems such as binary, octal, hexadecimal, and BCD, along with conversions. We saw how universal gates like NAND and NOR can implement any circuit. We examined digital circuit characteristics such as fan-in, fan-out, switching times, and noise margin. Finally, we introduced Boolean algebra, De Morgan's laws, and Canonical maps for circuit simplification. This module has laid the foundation. In the next module, we will build on this knowledge to design more advanced systems such as combinational and sequential circuits, programmable devices, and even simple CPUs.